Hello there, and welcome to Sleepy Science Vault. Somewhere out beyond the edge of what any telescope has ever seen, there is a question waiting. It has followed humanity through firelight and candlelight and now through the soft blue glow of 1,000 screens in 1,000 dark rooms. The question is simple to ask and almost impossible to answer. Is life something rare, a fragile accident tucked into one small corner of an indifferent universe? Or is it something deeper? Something woven into the very fabric of existence itself, so that the universe is not just a stage on which life happens to appear, but something closer to a living thing in its own right. Tonight, we are going to sit with that question. Not to answer it, but to explore it slowly, the way you might turn a strange and beautiful stone over in your hand, again and again, watching the light catch it differently each time. This is astronomy as a lullaby. Science as a quiet companion for the hours when the world grows still. So let yourself settle in. There is nowhere else you need to be right now, and nothing you need to solve. Just listen, and let the universe unfold at its own unhurried pace. We begin with the question itself, because it is worth understanding why this idea has captured so many imaginations across so many centuries. The appeal of a living universe comes from a very old tension. For most of scientific history, life has been treated as something local. Something that happens on planets, under the right conditions, given enough time and enough chemistry. Rare, precious, almost accidental. But there has always been another way of looking at things. What if life is not an interruption in an otherwise lifeless cosmos, but an expression of something the cosmos was always capable of? What if the difference between a rock and a redwood tree, between a cloud of hydrogen and a beating heart, is smaller than it seems? That is the heart of the question. Is life rare within the universe, or is it, in some deep and strange sense, built into it? It is important to say clearly, and gently, that this idea is not an established scientific fact. It is speculative. It lives mostly in the space of philosophy and theoretical thinking, rather than in the space of proven, testable science. When you hear people discuss the universe as if it were alive, they are usually not making a claim that can be measured in a laboratory. They are offering a way of seeing. A lens. A perspective that helps some thinkers make sense of patterns they find compelling, even if those patterns fall short of proof. This distinction matters, and we will return to it more than once tonight, because it shapes everything else. The living universe idea is less like a fact waiting to be confirmed, and more like a question waiting to be sat with. And there are real critics of this idea, thoughtful people who study the universe closely and remain unconvinced. Their central complaint is this: many living universe claims rely on analogy, rather than on direct evidence. An analogy can be beautiful. It can be illuminating. But it is not proof. If someone says the universe behaves like a living organism because both grow, and both change, and both seem to organize themselves, that is a comparison, not a demonstration. Two things can resemble each other on the surface while remaining fundamentally different underneath. Critics are careful to point this out, not to dismiss wonder, but to protect the difference between poetry and physics. A river can look like it is searching for the sea, curving and adjusting its path around obstacles. but we understand that the river is not making choices. It is simply following the laws of gravity and erosion. The resemblance to intention is an illusion created by our own pattern-seeking minds. So the question becomes, is the universe's apparent organization more like the river, shaped by blind physical law and only resembling life from a distance? Or is there something more happening? Something that goes beyond analogy into a deeper kinship with biology. Part of what makes this debate so persistent is that it hinges on a word we rarely stop to examine closely. The word life itself. We use it constantly and comfortably in our daily lives. We know life when we see it, or at least we think we do. A bird is alive. A stone is not. A forest is alive. A cloud is not. But push on that boundary even a little, and it starts to blur in unexpected ways. Is a virus alive? It cannot reproduce on its own, yet it carries genetic instructions and evolves over time. Is a flame alive? It consumes fuel, grows, and can even spread and reproduce itself across a landscape, yet almost no one would call fire a living thing. The living universe idea takes this uncertainty and stretches it as far as it can go. It asks us to consider whether the word life might describe not a special, rare category of matter, but a set of behaviors and patterns that could, in principle, appear at almost any scale, including the largest scale of all. This is precisely why the idea remains controversial, even among people who find it fascinating. It is not simply asking, is the universe alive, in the way you might ask, is that plant alive? It is quietly asking a much bigger question underneath. What do we actually mean when we say something is alive at all? Interestingly, this is not only the domain of poets and philosophers. Some biologists themselves have proposed unusually broad definitions of life. Definitions built not around specific biological details, like DNA or cells or carbon chemistry, but around abstract qualities. Qualities like the ability to maintain internal order against the pull of disorder, the ability to respond to change, the ability to sustain a persistent pattern over time, even as the specific material passes through it. Under a definition broad enough, almost any complex, self-sustaining, self-organizing system could be described using the language of life. And if you accept that kind of definition, then the universe, with its vast webs of matter and energy constantly organizing and reorganizing itself, becomes at least eligible for the conversation. Not proven to be alive, but no longer automatically excluded from the possibility, either. It is a strange kind of doorway. Not proof that the universe is alive, but a redrawing of the boundary, wide enough that the question is even allowed to be asked seriously. Now, here is something worth pausing on, because it is often misunderstood. Even if we accepted, for a moment, that the universe could reasonably be called alive in some broad sense, that would not mean the universe is conscious. It would not mean the universe thinks, or feels, or is aware of itself the way you are aware of yourself right now, listening in the dark. Being alive, in the broadest biological sense, is not the same as having a mind. A single-celled organism is alive. It responds to its environment, seeks resources, and maintains itself, but almost no one imagines it as having thoughts, or feelings, or a rich inner experience. So if the universe were alive in this broad, structural sense, it might simply mean the universe behaves like an extraordinarily complex, self-organizing system. Vast, intricate, responsive to its own internal conditions in some very abstract way. Not a mind gazing back at us from the darkness between galaxies. Just complexity. Deep, layered, almost unfathomable complexity, organizing itself according to patterns we are still struggling to fully understand. This distinction matters, because it keeps the idea grounded, even while it remains speculative. We are not talking about a cosmic being with intentions and desires. We are talking about the possibility that structure, pattern, and self-organization might run deeper through reality than we once assumed. And self-organization is where some of the most compelling arguments for this whole idea actually come from. Some writers point to self-organization as one of the strongest reasons to entertain the living universe idea at all. It is a genuinely remarkable feature of nature, that complex order can emerge without anyone designing it. Without a central planner. Without a blueprint drawn up in advance. Think of a flock of starlings, twisting and flowing through the evening sky in shapes that seem almost choreographed, yet no single bird is directing the group. Each bird is simply following a few small local rules, and from those simple rules, breathtaking complexity emerges. Snowflakes form intricate, symmetrical patterns from nothing more than water molecules following the basic physics of temperature and pressure. Galaxies spiral into elegant, sweeping arms, shaped by gravity acting on countless individual points of matter, with no architect guiding the design. This is the quiet magic at the center of the living universe idea. If complexity and order can emerge from simple rules, again and again, at every scale we look, from snowflakes, to flocks of birds, to spiral galaxies, then perhaps the universe has a natural tendency toward organizing itself. Not because it is planning anything, but because organization may simply be one of the deep, underlying tendencies of reality itself. And once you start looking through that lens, it becomes hard to completely unsee it. There is a specific, more technical concept that some thinkers connect to this idea. It comes from biology, and it is called autopoiesis. Autopoiesis describes a system that can sustain and reproduce its own organization. Not just persist passively, the way a rock persists, but actively maintain its own structure over time, even as the materials that make it up are constantly changing. A living cell is the classic example. Its molecules are replaced again and again throughout its life, yet the cell, as a coherent, organized pattern, continues on. Some thinkers have asked whether the universe might show something distantly similar. Not literal biological self-reproduction, but a kind of ongoing self-maintenance. Matter and energy flowing, transforming, recombining, forming stars, and then scattering their elements back into space when those stars die, only for that same material to gather again into new stars, new planets, and perhaps, new life. Is that autopoiesis in any meaningful sense? Most scientists would say, not really. Not in the strict biological definition. But as a loose, poetic parallel, it is not hard to see why the comparison catches people's attention. There is something in that endless cycle of formation, dissolution, and reformation that feels less like a machine simply running down, and more like a system, somehow, sustaining itself. This connects to a larger pattern in how the living universe idea is usually presented. It often functions less like a rigid theory, and more like a bridge. A bridge between two fields of knowledge that do not usually speak to each other very often: physics and biology. Physics tends to describe the universe in terms of forces, particles, and mathematical laws. Cold, precise, and impersonal. Biology tends to describe living things in terms of growth, adaptation, and self-maintenance. Warm, dynamic, and process-driven. The living universe idea borrows biology's vocabulary and applies it, carefully and speculatively, to the language of the cosmos. When someone describes the universe as growing, or evolving, or organizing itself, they are, in a sense, letting biological language cross over into a domain that has traditionally belonged to physics alone. This can be a powerful way of building intuition, of making the incomprehensibly vast feel a little more familiar, a little more relatable. But it also carries a risk. Because language shapes the way we think, borrowing biological words for non-biological processes can make something feel more alive than the underlying evidence actually supports. Still, this bridge building is part of what makes the idea so enduring, and so quietly beautiful, even for those who remain skeptical of its claims. Perhaps nowhere is that beauty more visible than in the very structure of the universe itself, at the largest scales we can observe. If you could zoom out far enough, far past galaxies, past galaxy clusters, out to the grandest scale astronomers can map, you would find something unexpected. The universe is not evenly scattered, like sugar stirred into water. Instead, matter gathers into vast filaments and clusters, stretched across unimaginable distances, separated by enormous, quiet voids. Astronomers call this pattern the cosmic web. Long, thread-like structures of galaxies and dark matter, connecting across space in a way that, when mapped out and visualized, bears a startling resemblance to something else entirely. The tangled, branching network of neurons inside a human brain. Of course, the two are built from entirely different materials, shaped by entirely different physical processes, gravity pulling matter together over billions of years on one hand, electrochemical signals firing between neurons on the other. The resemblance is almost certainly a case of similar mathematics producing similar shapes, rather than any direct, deeper connection. Branching, filamentary networks tend to emerge whenever you have nodes connected by pathways, competing for limited resources across space, whether those nodes are galaxies, or neurons, or even the roots of a tree, or the branches of a river delta. But even knowing this, it is hard not to feel something when you look at that image. The universe, on its grandest scale, loosely echoing the shape of the very organ we use to think, and wonder, and ask questions like the ones we've been asking tonight. Perhaps that resemblance means nothing more than shared mathematics. Or perhaps it is simply a beautiful coincidence, the kind the universe seems to produce again and again, at every scale, without any explanation required. Either way, It is a fitting image to rest on for a moment. A cosmic web, vast and quiet, humming with structure across the dark. And somewhere inside one small, glowing filament of that web, a small blue planet, spinning quietly, carrying within it the very question we began with tonight. We have only just begun exploring what it might mean for the universe to feel alive. In the next part of our journey, we will go further. We will look more closely at the patterns of growth and structure that stretch across the cosmos, and we will sit with new perspectives on complexity, emergence, and the strange, quiet order that seems to arise, again and again, out of chaos. For now, let this first collection of ideas settle gently in your mind, the way starlight settles over a quiet field at night. There is no need to reach any conclusions. No need to decide, tonight, whether the universe is alive in any real sense at all. Just let the question rest beside you, soft, open, and endlessly patient, as we continue, gently, into what comes next. Let's continue where we left off, drifting a little deeper into the architecture of the cosmos, and into the question of what holds it all together in the first place. Because so far, we have been talking about the visible universe. Stars, galaxies, the great glowing web of light stretched across billions of years. But there is another player in this story, one you cannot see directly, no matter how powerful your telescope. Astronomers call it dark matter. Dark matter does not shine. It does not reflect light, or block it, or interact with it in any way we can detect directly. We know it exists only because of its gravity, the way it tugs on galaxies, holding them together far more strongly than their visible matter alone could explain. Without it, galaxies would likely fly apart, spinning too fast for their own visible mass to contain them. In discussions about a living universe, dark matter is sometimes given a very particular kind of description. People call it an invisible skeleton. A hidden framework, holding the shape of cosmic structures together from within, the way bones hold up the soft tissue of a body, unseen beneath the surface, quietly doing the work of structure. It is a striking image, and an easy one to picture. But it is worth remembering, gently, that this is an analogy. A skeleton, in biology, is made of living tissue, grown by a body, serving a specific evolved purpose within an organism. Dark matter is something else entirely, a still mysterious form of matter, behaving according to gravity and physics, not biology. The comparison helps us visualize its role. It gives shape to something invisible and hard to imagine. But the resemblance ends at the level of function, not substance. Calling it a skeleton is a way of understanding through metaphor, not a claim that the universe has bones, in any literal sense. Still, once that image takes hold in the imagination, it becomes hard to shake. Somewhere out there, wrapped invisibly around and through every galaxy, is a hidden framework we cannot see, but that shapes everything we can. This idea of hidden structure fits naturally into a larger argument that supporters of the living universe idea often return to. And it centers on change. One of the simplest observations you can make about the universe is that it does not stay the same. It changes. It grows. It evolves, across spans of time so vast they are almost impossible to hold in the mind all at once. Stars are born, live out their long lives, and eventually die, scattering their material back into space. Galaxies form, collide, merge, and reshape themselves. The universe today looks nothing like it did in its first few 100,000 years, when it was little more than a hot, glowing fog of particles, with no stars or galaxies at all. Change, growth, and evolution, these are qualities we usually associate with living things. A seed becomes a tree. A child becomes an adult. A single cell divides and grows into something impossibly complex. Living systems, almost by definition, do not stay static. They unfold, over time, into something different than what they began as. So when supporters of the living universe idea point to the sweeping changes across cosmic history, the birth of stars, the shaping of galaxies, the slow unfolding of structure from simplicity into complexity, they are drawing a very natural, very human connection. If change and growth are hallmarks of life, and the universe is defined by change and growth on the grandest scale imaginable, then perhaps that resemblance is worth taking seriously, even if it cannot be proven. Of course, change alone does not prove life. Weather changes. Coastlines change. Mountains rise and erode away over millions of years, without anyone suggesting they are alive. But there is one particular kind of change happening across the universe that draws a more specific, and more provocative, comparison. And that is expansion. We know, from decades of careful observation, that the universe is expanding. Space itself is stretching, carrying galaxies farther apart from one another as time goes on, not because galaxies are moving through space, like ships sailing across an ocean, but because the space between them is growing, quietly, continuously, in every direction at once. Some writers have looked at this expansion, and reached for a very particular biological word to describe it: growth. Or sometimes, metabolism. In living organisms, growth involves an increase in size and complexity over time, fueled by the intake, transformation, and use of energy. Metabolism is the underlying process making that growth possible, the constant chemical activity inside a living body, converting one form of energy into another, building up and breaking down, again and again, to sustain life. When writers compare cosmic expansion to growth, or to metabolism, they are drawing on this deep, biological association. The universe is not sitting still. It is expanding outward, continuously, the way a living thing might grow larger over the course of its life. It is, again, an analogy, a way of borrowing familiar biological language to describe something that operates on a scale and by mechanisms almost entirely unlike anything in biology. Cosmic expansion is driven by the fundamental properties of space itself, not by cellular division, or nutrient absorption, or any biological process we understand. But the comparison persists, because on some intuitive level, it resonates. Something is growing outward, continuously, across billions of years, whether we call it expansion, or something closer to life. And expansion is not the only place where this metabolic language appears. There is another, perhaps even more compelling parallel, found not in the growing space between galaxies, but in the ongoing transformation of matter and energy throughout the cosmos. Because the universe, in its own quiet way, is constantly recycling itself. Stars form from vast clouds of gas and dust, drawn together by gravity over long stretches of time. Inside their cores, through the immense pressure and heat of nuclear fusion, they transform simple elements into heavier ones, hydrogen into helium, and eventually, over the long lives of certain stars, into carbon, oxygen, iron, and more. When those stars eventually die, some quietly fading, others exploding in the brilliant violence of a supernova, they scatter those newly formed elements back out into space. That scattered material does not simply disappear into the void. It becomes the raw ingredients for the next generation of stars. It gathers again, drawn together by gravity, forming new stars, new planetary systems, and in at least one case that we know of, new life. This is where the metabolic comparison becomes especially interesting to those exploring the living universe idea. In a living body, metabolism involves transformation and reuse. Nutrients are broken down, absorbed, transformed into new structures, and eventually, the body sheds what it no longer needs, so that the cycle can continue. Some writers see a striking, almost poetic parallel in the way matter and energy are constantly transformed and reused throughout the cosmos, broken down inside stars, scattered by their deaths, and gathered again into new forms, endlessly, across billions of years. Matter that was once part of an ancient, long-dead star may now be part of a mountain, or a river, or, quite literally, part of your own body. That is not poetic exaggeration. It is a fact well established by astrophysics. Much of the carbon, oxygen, and iron inside you was forged inside the heart of a star that lived and died long before our solar system even existed. In a very real, very physical sense, you are made of recycled starlight and stardust. Whether or not that qualifies, technically, as metabolism in the biological sense, it is hard to deny the poetry of it. Matter flowing endlessly through stars, through dust, through planets, being broken down and rebuilt again and again, across a canvas of time so vast it barely fits inside the imagination. This constant cycling of matter through stars and dust has led some thinkers to describe the process using an even broader phrase, a cosmic life cycle. Galaxies form. They grow, sometimes merging with neighboring galaxies in slow, gravitational dances that can take hundreds of millions of years to complete. New stars are born from the gas stirred up by these mergers. Old stars die, seeding the surrounding space with new material. Over time, galaxies change shape, evolve in structure, and pass through different stages, not unlike the way a living organism might pass through different stages of life, youth, maturity, and eventual decline. Framing this as a life cycle is, once again, a choice of language, a way of imposing a familiar biological structure onto processes governed entirely by gravity, nuclear physics, and time. Galaxies do not choose to grow, or to merge, or to age, the way living things make choices, or follow biological programming written into their genes. And yet, the parallel remains oddly satisfying to trace. Birth, growth, transformation, and eventual quiet fading, it is a pattern that appears, again and again, whether we are looking at a single star, an entire galaxy, or a living creature drawing its final breath. Some who explore this idea take it a step further still, arguing that individual galaxies and star systems should not be thought of as isolated objects at all, but as component parts of something larger. In this framing, a single star system is not simply floating alone in space, disconnected from everything around it. It is treated more like an organ within a much larger organism, a small, functioning part contributing to some larger process it may not even be able to comprehend from the inside. This is, admittedly, one of the more speculative and philosophically loaded corners of the living universe idea. Most mainstream astronomers would be quick to point out that there is no evidence of galaxies cooperating with one another, or serving some greater cosmic function, the way organs cooperate within a body to keep an organism alive. Galaxies interact through gravity alone, following simple physical laws, with no larger coordinating plan behind their behavior. But the appeal of this framing lies less in its scientific precision, and more in the way it reshapes our sense of scale and our sense of belonging. If galaxies and star systems are, in some loose sense, parts of a greater whole, then so, too, is everything within them. Every planet, every quiet, starlit night sky, including, perhaps, us. This brings us to one of the more ambitious threads running through many of these theories, an attempt to draw everything, from the smallest particle to the largest galaxy, into a single, continuous story. Rather than treating galaxies, stars, planets, and living things as entirely separate categories of existence, some of these frameworks propose that they are simply different levels, or different layers, of one ongoing cosmic process. Atoms come together to form molecules. Molecules come together to form the building blocks of stars, and planets, and eventually, given the right conditions, life itself. Life, in turn, becomes complex enough to form ecosystems, then civilizations, then, perhaps eventually, ideas and questions like the ones we are exploring together right now. In this view, there is no sharp, absolute line separating non-living matter from living matter. There is simply a long, continuous unfolding, where complexity accumulates, layer upon layer, across enormous stretches of time. Atoms become molecules. Molecules become chemistry. Chemistry, under the right conditions, becomes biology. Biology, given enough time, becomes minds capable of looking upward into the night sky, and asking where they came from. This is part of what makes the universe, in this broader view, look less like a fixed, static backdrop, and more like a developing system. Something quietly unfolding, layer by layer, scale by scale, moving from simplicity toward ever greater complexity, without any obvious ceiling or endpoint in sight. Which brings us to a particularly thoughtful framing that some researchers have proposed, describing the universe not simply as alive, in any literal biological sense, but as something closer to an evolutionary development system. This framing borrows a careful balance from biology itself. Evolution, as we understand it in living organisms, is not a purely random process, nor is it a purely directed one. It involves random variation, small, chance changes, occurring without any particular goal in mind. But it also involves a kind of directional shaping, through natural selection, where certain variations persist and accumulate over time, because they happen to work well within their environment. Some researchers propose that the universe, in its long unfolding from the simplicity of its earliest moments to the intricate complexity of galaxies, stars, planets, and life, may involve a similar interplay. Randomness, at the level of quantum fluctuations, and chaotic stellar processes, and unpredictable collisions between cosmic bodies. But also, over long enough timescales, a kind of directional tendency toward greater complexity, greater structure, greater organization, arising again and again out of that underlying randomness. Not directed, in the sense of intention or design, but directional, in the sense that complexity does seem to accumulate, layer upon layer, as time moves forward. Whether that pattern reflects something deep and meaningful about the nature of reality itself, or whether it is simply what happens, mathematically, when physical laws are given billions of years and vast amounts of matter and energy to work with, remains an open question. Perhaps the most open question of all. And it is a question we will keep gently circling, as we continue moving through this long, quiet night together. For now, let this settle. Matter flowing through stars, then scattering, then gathering again. Galaxies changing shape across unimaginable stretches of time. Complexity slowly rising, layer by layer, from atoms to ecosystems to galaxies themselves. In the next part of our journey, we will turn towards some of the more intricate patterns of complexity within the universe itself, exploring what emergence really means, and how the smallest, simplest rules can give rise to structures of astonishing scale and beauty. For now, simply rest here for a moment, in this vast, unfolding process, and let the weight of the day continue to drift gently away, as the story of the cosmos continues on, quietly, into the dark. Let's sit with that idea for a moment longer, because it opens onto something even more specific, a distinction that some researchers consider essential to understanding what a living universe might actually mean. That distinction is the difference between evolving and developing. In everyday language, we often use these words interchangeably. Something evolves, something develops, and we tend to picture roughly the same process either way: change, over time, moving towards something more complex. But within certain cosmic evolution models, these two words are pulled apart quite deliberately, because they describe two very different kinds of pattern. In this framework, the universe is not simply evolving, in the loose sense of changing over time. It may also be developing, and development implies something more specific. It suggests long-term patterns that look more ordered, more structured, than what you would expect from chance alone. Not randomness accumulating into complexity by accident, but something closer to an unfolding sequence, following its own internal logic, the way an acorn unfolds, step by step, into the specific, recognizable shape of an oak tree. This is a subtle distinction, but an important one. And it is worth taking a little time to understand clearly. Some researchers working in this space of cosmic evolution draw a very careful line between these two concepts. Evolution, in the biological sense we usually mean, requires something quite specific: reproduction, along with variation. Living organisms reproduce, passing on their traits to offspring, and small variations arise in that process, some helpful, some not, and over many generations, natural selection favors the variations that work best. Without reproduction and variation happening together, over multiple generations, you do not really have evolution in the strict biological sense. Development is different. Development does not necessarily require reproduction at all. Development is more about the way a single system, a single body, a single unfolding process, moves through stable, structured stages over time, the way an embryo develops into a fully formed organism, following a coherent internal pattern, without needing to reproduce or select between different variations along the way. So when some writers say the universe might be developing, rather than strictly evolving, they mean something quite specific. They are suggesting the universe may be moving through structured, ordered stages, not because different versions of the universe are competing and being selected for, the way species compete in an ecosystem, but because there may be some coherent, internal pattern, unfolding steadily across cosmic time. This distinction becomes especially interesting when we ask a very practical question, which is easier to actually observe. Universal evolution, or universal development. Some writers argue quite persuasively that universal development is the easier of the two ideas to study, and to take seriously as a subject of genuine inquiry. Why? Because evolution, in the strict biological sense, typically requires comparing many different examples across generations, many organisms, many variations, many outcomes, to see which patterns persist and which fade away. But we only have one universe to study. There is no second universe sitting nearby, with slightly different starting conditions, that we can compare ours against, to see which patterns were favored by some cosmic selection process. Development, on the other hand, can be studied within a single system, unfolding over a very long time scale. We can watch, in principle, how the universe has moved from its early, simple, undifferentiated state, through the formation of the first atoms, then stars, then galaxies, then planets, then, eventually, the complex chemistry that gave rise to life. That is a single, continuous unfolding, observable through the evidence left behind in light, and in matter, and in the structure of the cosmos itself. It does not require comparing our universe to other universes. It only requires patient observation of the one universe we actually have. This is part of why some thinkers find the language of development more scientifically approachable than the language of evolution, when it comes to describing the universe as a whole. It sidesteps some of the trickiest philosophical problems, while still preserving that sense of a coherent, unfolding, structured process, playing out across billions of years. Of course, none of this suggests that the universe unfolds with rigid, predetermined certainty, following one single fixed path with no room for chance or surprise. And this is where a broader systems approach becomes useful, one that tries to hold both possibilities together at once. This approach suggests that the universe could have both contingent and deterministic features, existing side by side, not as a contradiction, but as a natural kind of complexity. Contingent simply means something that could have gone differently, depending on small, unpredictable events along the way. Deterministic means something that follows a fixed, predictable pattern, governed by consistent underlying rules. Living systems, interestingly, tend to show exactly this same blend. Consider the growth of a single tree. The overall pattern of its development is fairly deterministic. Seeds of a particular species will reliably grow roots, then a trunk, then branches, following broadly predictable stages, governed by their genetic programming. But the exact shape of any individual tree, the precise angle of each branch, the specific pattern of its leaves, the particular direction it leans as it reaches for sunlight, those details are highly contingent, shaped by countless small, unpredictable factors along the way. Wind, soil conditions, the shade of a neighboring tree. No two trees, even of the same species, ever grow in exactly the same shape. Some thinkers propose that the universe might follow a similar pattern. Broad, deterministic laws, gravity, thermodynamics, the fundamental physics governing how matter and energy behave, shaping the large-scale, reliable structure of cosmic development. But within that structure, countless contingent details, the exact placement of galaxies, the specific history of any one star system, the particular sequence of events that led to life arising on one small, blue planet, shaped by chance, by small variations, by the countless unpredictable turns a complex system can take. Both deterministic order and contingent chance, weaving together, at every scale. This blending of order and chance is part of why researchers and writers exploring these ideas so often reach for language drawn from a particular field, systems theory. Systems theory is, at its core, the study of how complex wholes emerge from many interacting parts. It is used across an enormous range of disciplines, in biology, in ecology, in engineering, in economics, even in the study of weather patterns and climate. What ties all of these applications together is a shared interest in one particular phenomenon. The way order, structure, and complex behavior can emerge, from the bottom up, through the interactions of many individual parts, without requiring any single master controller sitting at the top, directing everything according to some grand plan. This is precisely the kind of order that seems to appear throughout the cosmos. No central intelligence is directing the formation of galaxies, or orchestrating the movement of stars, or deciding how matter should organize itself across the universe. And yet, order emerges anyway, intricate, beautiful, structured order, arising simply from the interactions of countless individual particles, governed by a small handful of consistent physical laws. This is why the language of systems theory fits so naturally into discussions of a living universe. It offers a vocabulary for describing exactly this kind of decentralized, emergent order that arises not from top-down design, but from the accumulated, patient interaction of countless smaller parts, each simply following its own local rules. And this idea of interconnected parts, working together to create something larger than any individual piece, leads naturally into one of the more recent, and more intriguing, directions this whole field of thought has taken. Some recent discussions in this space have moved toward describing reality itself as fundamentally relational. This is a subtle but genuinely fascinating shift in perspective. For a long time, especially in classical physics, the universe was often described primarily in terms of objects. Particles, planets, stars. Discrete things, existing in space, occasionally interacting with one another, but each treated, in a sense, as its own separate, isolated entity. A relational view of reality suggests something quite different. It suggests that the connections between things, the relationships, the interactions, the flows of information and energy between objects, may matter just as much, or perhaps even more, than the objects themselves. In this view, a particle is not fully understood simply by describing its individual properties, in isolation. It is understood by understanding how it relates to, and interacts with, everything around it. This shift toward relational thinking connects surprisingly well with our living universe theme. If life itself is fundamentally about relationships, the relationship between an organism and its environment, between individual cells within a body, between predator and prey within an ecosystem, then a relational universe, one where connection matters as much as substance, starts to feel a little closer to something we might recognize as alive. Not because of what the universe is made of, but because of how everything within it relates, and connects, and depends upon everything else. This relational thinking has increasingly drawn the living universe framework toward a rather unexpected new companion in recent years. Not just biology, but information theory. Information theory, broadly speaking, is the study of how information is measured, transmitted, and processed. It emerged originally from engineering and communication technology, but its core ideas have since spread into an enormous range of fields, including physics, biology, and cosmology. At its heart, information theory treats patterns, structure, and relationships as fundamental things worth studying in their own right, not simply as descriptions layered on top of physical matter, but as something meaningful and measurable in themselves. The living universe framework has increasingly borrowed from this way of thinking, precisely because it fits so naturally with the relational perspective we just explored. If structure and relationship matter as much as substance, then information, which is, in a sense, simply a measure of structure and relationship, becomes a natural lens through which to view the whole cosmos. Not just matter and energy, moving and transforming according to physical law, but patterns and information, flowing and processing, throughout the universe as a whole. This has led some thinkers to compare the universe to something quite different from the biological metaphors we explored earlier in our journey tonight. Not simply an organism, growing and metabolizing, but a giant network, processing information, in a way that echoes, at least loosely, the way individual cells process biochemical signals within a body, or the way neurons process electrical signals within a brain. In this framing, the universe is not simply a vast collection of matter, scattered through space. It is something closer to a vast, interconnected web of information, constantly being processed, transformed, and passed along, through the physical interactions of matter and energy at every scale, from the smallest particle exchanging a quantum of energy, to the largest galaxy cluster, gravitationally influencing its neighbors across millions of light years. This idea, understandably, leads to one of the more provocative questions within this entire field of exploration. If the universe really can be described, in some meaningful sense, as a system that processes information, does it have enough information processing capacity to be described as something closer to computational? Or, more provocatively still, something closer to mind-like? Some researchers have genuinely explored this question, using careful, mathematical approaches, attempting to estimate the theoretical information processing capacity of the universe as a whole, treating the interactions of every particle across the entire observable cosmos as a kind of vast, distributed computation. The results of this kind of thinking remain deeply speculative and very far from settled science. But the fact that serious researchers are even willing to ask the question, to seriously consider whether the universe's staggering complexity might resemble computation, or something loosely mind-like, shows just how far this broader living universe conversation has traveled, from its more modest, philosophical beginnings. Perhaps the universe is simply matter and energy, following consistent physical laws, across an almost incomprehensible span of time and space. Or perhaps, when matter and energy are woven together in a system this vast, and this intricate, and sustained across billions of years, something resembling structure, and relationship, and even the faintest whisper of information processing, begins to emerge on its own, without anyone designing it that way. We do not need to resolve that question tonight. It is enough, simply, to let it settle quietly in the mind, the way a distant thought settles gently before sleep, present, and open, and unresolved, drifting somewhere just beneath the surface of conscious thought. In the next part of our journey together, we will continue exploring this rich territory, moving from questions of information and computation, towards some of the more specific scientific ideas and historical figures who have shaped this ongoing conversation about the nature of the cosmos. For now, simply rest here, in this quiet idea of a relational, interconnected universe, connections upon connections, patterns upon patterns, stretching outward into the dark, farther than the eye, or even the mind, can fully follow. Let's continue drifting deeper into this territory, because from here, the conversation shifts slightly. We move from questions of structure and information, towards something even more intimate. Toward memory, and toward mind itself. One of the more evocative claims made by advocates of the living universe idea is the suggestion that the universe may possess something like memory. Not memory in the way you or I experience it, no vivid recollections, no images stored somewhere in the darkness between galaxies. Rather, this idea points to something more structural. The suggestion is that later cosmic structures could be shaped, in meaningful ways, by earlier cosmic events. That the universe, in its unfolding, carries forward traces of its own history, embedded within the patterns it produces. In a sense, this is not entirely unfamiliar, even in mainstream physics. The particular ratio of elements found in the universe today, the abundance of hydrogen, helium, and trace amounts of lithium, is a direct consequence of conditions in the first few minutes after the Big Bang. The specific patterns visible in the cosmic microwave background, that faint afterglow of light left over from the universe's early years, still carry subtle imprints of tiny fluctuations that occurred an incomprehensibly short time after everything began. In this sense, the universe does, quite literally, carry forward evidence of its own past, encoded within its present structure. Advocates of the living universe framework take this a step further, using the language of memory more deliberately. If a living organism's present state is shaped by its past, by its development, its experiences, its history, and the universe's present state is likewise shaped by its own long unfolding history, then perhaps memory, understood broadly enough, is not so foreign a concept to apply to the cosmos after all. Not conscious memory, not recollection, but a kind of structural memory, where the past leaves its quiet fingerprints on everything that follows. This question of memory leads naturally toward an even deeper and more contested territory: the question of consciousness itself. There is a particular philosophical idea, worth pausing on carefully, called panpsychism. It is not new. Its roots stretch back through centuries of philosophical thought, long before modern cosmology even existed. But it has found renewed relevance within living universe discussions in recent years. Panpsychism suggests something quite radical when you first encounter it. It proposes that consciousness might be a basic, fundamental feature of reality itself, not something that only emerges within complex brains, built from billions of interconnected neurons, but something present, in some minimal, foundational form, throughout all of existence. Under this view, consciousness would not be something brains create out of nothing. It would be something brains focus, and organize, and amplify, much the way a lens does not create light, but gathers and concentrates light that was already present. This is, admittedly, one of the more difficult ideas to hold in the mind comfortably. It does not suggest that a rock, or a raindrop, or a single hydrogen atom, experiences the world the way you do, with thoughts, and memories, and a rich inner narrative. Rather, it suggests something more like a faint, foundational quality, present at the smallest scales of reality, that becomes richer, and more complex, and eventually recognizable as something like awareness, only when organized into sufficiently complex systems, like a living brain. Panpsychism remains a minority position, even among philosophers who study consciousness closely. But it persists, generation after generation, precisely because it offers one possible answer to a question that has resisted every other approach so far. Namely, how does subjective experience arise at all, from purely physical matter? If consciousness is fundamental, rather than emergent, that particular puzzle shifts into an entirely different shape. Closely related to panpsychism, though distinct from it, is another idea that appears often in these discussions. It is called biocentrism. Biocentrism makes a bold, and deliberately provocative, claim. It argues that life, and consciousness, are not incidental byproducts of the universe, small, rare accidents that happen to occur here and there, scattered sparsely across an otherwise indifferent cosmos. Instead, biocentrism proposes that life and consciousness are central to how reality itself is structured. Not an afterthought. Not a side effect. But, in some sense, the very point around which reality is organized. This is a significant departure from the more conventional scientific view, which generally treats the physical universe as existing independently, following its own laws, indifferent to whether life happens to arise within it or not. Under this conventional view, life is simply what happens, occasionally, when the right physical and chemical conditions align, in the right place, for long enough. Biocentrism turns that relationship around. It suggests that reality, in some deep sense, may depend upon consciousness, rather than consciousness simply depending on reality. This is, without question, one of the more contested and controversial ideas within this entire field of exploration. Most physicists and cosmologists remain deeply skeptical of biocentrism, precisely because it is difficult to test, and because it inverts a relationship that is generally proven reliable and productive within conventional science. But biocentrism persists in these broader living universe discussions because it offers a compelling, almost poetic, answer to a very old and very human question. Why does the universe seem so remarkably suited for something like us to eventually come into being and look back up at the stars? Part of what fuels this line of thinking comes from a curious and genuinely strange feature of physics itself, the role that observation seems to play at the smallest scales of reality. In quantum mechanics, there is a long-standing and still deeply debated puzzle involving the behavior of particles at the smallest scales. Under certain interpretations, a quantum system can exist in a strange, undetermined state, not simply unknown to us, but genuinely unresolved, holding multiple possibilities simultaneously, until the moment it is measured or observed. Only at the moment of observation does that system appear to settle into one definite, specific outcome. This has led some thinkers, within living universe discussions, to treat observation itself as something deeply significant, arguing that reality, at its most fundamental level, may be shaped, in some meaningful way, by the act of being measured or perceived. Not created out of nothing by observation, necessarily, but somehow completed or resolved through that act of measurement. It is important to say, gently and clearly, that this remains one of the most debated interpretations within quantum physics itself, and many physicists strongly disagree with framing observation in terms of conscious perception at all. Measurement, in most rigorous physics, does not necessarily require a conscious mind. It can simply mean physical interaction with any other system, conscious or not. But the philosophical door remains open, just slightly, for those inclined to walk through it. The suggestion that observation, and perhaps even consciousness itself, might play some deeper, more active role in shaping physical reality than we have traditionally assumed. Taken together, these threads, memory, panpsychism, biocentrism, the strange role of observation, they converge toward one of the more sweeping claims made within this broader living universe conversation. And that is the idea that consciousness, life, and the cosmos itself may all share the same underlying origin. Rather than treating consciousness as something that appeared late and locally, only after billions of years of purely physical, mindless cosmic evolution, this framing suggests that consciousness may have been present, in some latent, foundational form, from the very beginning. Woven into the same fabric, the same origin point, as matter, energy, space, and time themselves. Under this view, life and mind are not strange, unlikely accidents, arising against tremendous odds, within an otherwise indifferent universe. They are simply the universe, gradually becoming aware of itself, through the slow unfolding of its own inherent potential. It is a beautiful idea, whether or not it turns out to be true in any literal, scientific sense. And it connects naturally to another claim, made by a number of thinkers within this space, the idea that the universe may be evolving, quite specifically, toward greater complexity, in a manner strikingly similar to the way life evolves here on Earth. We know, from the fossil record, and from the broader sweep of evolutionary biology, that life on Earth has, generally speaking, trended toward greater complexity over time, not in every single case, and not without countless setbacks, extinctions, and dead ends along the way, but broadly, across the full arc of evolutionary history. Simple, single-celled organisms gave way, eventually, to more complex, multicellular life. Simple nervous systems gave way, eventually, to brains capable of memory, learning, and eventually, self-reflection. Some thinkers propose that the universe as a whole may follow a broadly similar trajectory. From the extreme simplicity of its earliest moments, a hot, undifferentiated soup of particles, with no structure at all, toward the extraordinary complexity we observe today: stars, galaxies, planets, chemistry, biology, and minds capable of contemplating their own origins. If life on Earth trends toward complexity, and the universe as a whole seems to display a similar trend, at a much faster scale, then perhaps this is not simply coincidence. Perhaps it reflects something deeper and more fundamental about the underlying nature of reality itself. This naturally connects to the claim, made by several of the thinkers we have already discussed tonight, that the cosmos does not unfold randomly, but instead follows a deep, developmental pattern, reinforcing that earlier distinction we explored, between blind evolutionary chance, and something more like guided, structured development. And this developmental framing brings us, quite naturally, to one of the most persistent and thought-provoking arguments within this entire field. An argument centered on what physicists call fine-tuning. The physical constants that govern our universe, the strength of gravity, the precise balance between the forces that hold atomic nuclei together, the specific rate of cosmic expansion in those crucial first moments after the Big Bang, are extraordinarily, almost uncomfortably, precise. Even very small variations in these fundamental constants, changes far too small to easily imagine, would likely have resulted in a universe incapable of forming stable stars, or complex chemistry, or anything remotely resembling the conditions necessary for life to ever arise. This observation, often called the fine-tuning problem, has puzzled physicists and philosophers alike for decades. Why does the universe happen to have exactly the right conditions, out of an almost infinite range of possible conditions, to allow for the eventual emergence of stars, planets, chemistry, and life? Some writers, working within the living universe framework, argue that this remarkable fine-tuning makes far more intuitive sense if the universe is understood as part of some larger, lifelike developmental process, rather than as a purely random, purposeless arrangement of matter and energy that simply happened, against staggering odds, to land in exactly the right configuration for something like us to eventually exist. This is, without question, one of the more persuasive threads running through this entire body of thought, at least on an intuitive, emotional level, even though it remains, like everything else we have explored tonight, deeply speculative, and far from settled within mainstream physics. Taken all together, this entire body of ideas, memory, consciousness, biocentrism, fine-tuning, developmental complexity, often gets framed as something larger than the sum of its individual claims. It becomes, in the hands of its strongest advocates, a direct challenge to a very old and very common assumption. The assumption that life is simply a local accident, confined to one small, unremarkable planet, orbiting one ordinary star, among billions upon billions of other stars, scattered indifferently throughout an otherwise lifeless cosmos. The living universe framework asks us, gently but persistently, to consider another possibility. That life, and perhaps even mind, are not accidents at all. That they may be, in some deep and still poorly understood sense, woven into the very structure and unfolding of reality itself, present, in potential, from the very beginning, waiting patiently across billions of years, for the right conditions to finally bring them into being. This entire way of thinking has, in recent years, increasingly found a home within a broader, more formal area of research, known as cosmic evolution. This field brings together astronomers, physicists, chemists, and biologists, all working to understand the universe's long unfolding history as a single, connected, continuous process, treating the formation of stars, the formation of planets, and the eventual emergence of life, not as separate, unrelated events, occurring by chance in isolated corners of the cosmos, but as different stages, within one long, deeply interconnected story. It is a story that stretches back nearly 14 billion years, from the almost unimaginable simplicity of the universe's very first moments, all the way forward, to this exact moment, right now, to you, resting quietly in the dark, listening to this story unfold, carrying within your own body atoms that were forged inside ancient, long-vanished stars. We have covered a great deal of ground tonight: memory, mind, biocentrism, fine-tuning, and the long, patient unfolding of cosmic complexity. There is still more of this story left to explore together, in the segments still ahead. For now, let all of this settle quietly, the way sediment settles slowly through still water, drifting gently downward, layer upon layer, undisturbed. There is no need to hold on to every detail. Only to rest, here, in the quiet immensity of the questions themselves, and to let the universe continue turning, slowly, patiently, in the dark, as we drift together toward whatever comes next. We left off with the long, unfolding story of cosmic evolution, one continuous thread stretching from the earliest moments after the Big Bang, all the way to this quiet moment now. Let's follow that thread a little further. Some of the more recent writing in this field treats cosmic evolution not simply as an interesting metaphor, but as a genuinely broad, unifying framework. Under this framework, stars, galaxies, and life are not separate subjects, studied in isolation by separate branches of science. They are treated as connected stages, within one single, continuous, unfolding story. This is, in some ways, a shift in perspective as much as it is a shift in evidence. For a long time, astronomy studied the stars and galaxies. Biology studied life. Chemistry studied the interactions in between. Each field, developing its own vocabulary, its own methods, its own careful boundaries. Cosmic evolution, as a broader framework, tries to draw these separate threads back together, treating the birth of stars, the formation of planets, and the eventual emergence of living things, as different chapters within the very same story, rather than as unrelated subjects that simply happen to occur within the same universe. There is something quietly powerful in that reframing. It suggests that the same underlying processes, the same patient unfolding of complexity over time, connects the birth of a star, to the formation of a planet, to the emergence of the first living cell, to the eventual appearance of a mind capable of understanding any of it at all. This connects closely to another shift in how modern thinkers describe the universe's long-term changes. Rather than comparing cosmic history to simple mechanical motion, the way a clock ticks forward, predictably, according to fixed and simple rules, modern discussions increasingly reach for a different kind of comparison. They compare the universe's long-term changes to developmental stages, borrowed directly from biology. This is a meaningful difference in language and in meaning. A mechanical system, like a clock or a simple pendulum, moves forward in a fairly repetitive, predictable way. Nothing fundamentally new emerges from its motion. It simply repeats the same basic pattern, again and again, indefinitely. Development, by contrast, implies something different. It implies stages. Distinct phases, each one building upon what came before, each one qualitatively different from the last, moving toward increasing complexity and differentiation, the way an embryo moves through distinct developmental stages, on its way toward becoming a fully formed, complex organism. When modern cosmologists and writers describe the universe using this developmental language, they are suggesting something more than simple, repetitive motion. They are suggesting a genuine unfolding, moving through distinct phases. From an early universe of pure energy, to a universe of simple particles, to a universe of atoms, to a universe of stars, to a universe rich with galaxies, planets, chemistry, and eventually, life. Each stage, distinct. Each stage, building upon what came before it, in ways that feel less like mechanical repetition, and more like biological growth. Part of what has encouraged this shift in language is a broader shift in how physicists and cosmologists have come to understand the universe itself over the past century. For a very long time, going back centuries, the prevailing scientific view treated the universe as fundamentally static. Fixed. Unchanging, on the largest scales, even as individual stars and planets within it moved and shifted. This was, in many ways, a comfortable, intuitive assumption. The night sky, after all, looks largely the same, night after night, year after year, across an entire human lifetime. It is easy to assume that stillness reflects the deeper nature of the cosmos as a whole. But over the past century, that assumption has been overturned, decisively, by careful observation. The universe, we now understand with a very high degree of confidence, is not static at all. It is dynamic. It has a history. It began in a hot, dense state, and it has been expanding, changing, and evolving ever since. Galaxies are not fixed points, hanging permanently in an unchanging sky. They are moving, colliding, merging, and drifting apart from one another, as space itself continues to stretch and grow. This shift, from a static universe to a dynamic one, has quietly reshaped the entire philosophical landscape surrounding these living universe discussions. Some recent writing emphasizes precisely this point, that the universe simply seems more dynamic, more active, more prone to genuine change and transformation than the older static models ever assumed. And that shift, in turn, makes lifelike interpretations of the cosmos feel considerably more plausible, to at least some thinkers, than they would have seemed under the older, more static picture of reality. If the universe is static and unchanging, lifelike comparisons feel like a strange, poetic stretch, applied to something fundamentally still and fixed. But if the universe is genuinely dynamic, constantly changing, constantly unfolding, constantly moving through new configurations and structures over time, then comparisons to living systems, which are themselves defined by constant change and transformation, begin to feel a little less like poetic exaggeration, and a little more like a reasonable, if still speculative, way of describing what we actually observe. This dynamic, ever-changing quality of the universe is precisely why lifelike interpretations of cosmology keep reappearing, generation after generation, among different thinkers, working from different angles, and arriving, again and again, at strikingly similar intuitions. One of the more startling and imaginative extensions of this dynamic, evolving universe concept, comes from a theory known as cosmological natural selection. This theory proposes something genuinely remarkable, the idea that universes themselves might reproduce and evolve over time, in a manner loosely analogous to the way living organisms reproduce and evolve, through the familiar biological mechanism of natural selection. Except, in this case, the organisms being selected are not individual creatures, but entire universes. Cosmological natural selection suggests, quite specifically, that black holes could act as a kind of reproductive mechanism for new universes. To understand why this idea emerged at all, it helps to remember what a black hole actually represents in modern physics. A black hole forms when a massive star collapses in on itself, under the crushing weight of its own gravity, compressing an enormous amount of matter into an incomprehensibly small, dense point. At the very center of a black hole, according to our current mathematical models, our usual understanding of space and time appears to break down entirely. Some theoretical physicists have proposed that rather than representing a true, final endpoint, where everything simply ceases to exist, the extreme conditions at the center of a black hole might instead trigger something else entirely, a kind of bounce, or rebound, giving rise to an entirely new, expanding region of space and time on the other side. In other words, some speculative models suggest that black holes might not be endings at all. They might be beginnings, doorways, quietly giving birth to entirely new universes, hidden away, inaccessible to us, on the other side of that boundary. If this idea is correct, even in a general sense, it suggests a genuinely extraordinary possibility. That black holes are not simply a strange and violent endpoint for massive dying stars, but might actually function as a kind of reproductive mechanism for the universe as a whole. Each black hole, in this framework, becomes a potential seed for an entirely new universe, budding off quietly from our own. This leads directly to one of the more imaginative claims made by some authors working within this theoretical framework, the suggestion that our universe may not be a singular, one-time event at all. Instead, it may represent just one generation, within a much longer lineage, stretching backward and forward through an almost unimaginable succession of universes, each one giving rise, through its black holes, to new generations of universes that follow it. Under this view, our own universe could be understood as one of many offspring universes, born from the black holes of some earlier, parent universe, rather than as a singular, unique event, occurring once, and never repeating. It is, admittedly, one of the more speculative and mathematically abstract ideas within this whole broad field of cosmological thought. It cannot currently be tested directly, since we have no way to observe conditions on the other side of a black hole's boundary, nor any way to observe other universes, if they do, in fact, exist. But it remains a serious subject of theoretical inquiry among some physicists, precisely because it offers an elegant, internally consistent way of explaining certain deep puzzles in cosmology, including, intriguingly, some aspects of that fine-tuning problem we explored earlier tonight. If universes really do reproduce, through some process resembling natural selection, then perhaps, over countless generations, the physical constants that make stars, and black holes, and eventually life possible, become slightly more common, slightly more prevalent, across successive generations of universes, not because any conscious force is guiding the process, but simply because universes that produce more black holes, produce more offspring, and so those particular physical conditions, quite naturally, become more widespread over time. A kind of Darwinian selection, operating not on living organisms, but on the very physical constants that shape entire universes. This entire framework leads to an even broader, and even more speculative model, proposed by some theorists working at the very outer edges of cosmology. The idea that the universe, as a whole, might be understood as genuinely self-reproducing, meaning it might generate entirely new universes, from within itself, again and again, indefinitely, stretching outward, both backward and forward, through what could potentially be an endless, branching lineage. In this particular model, black holes are treated, quite specifically, as possible gateways, quiet, hidden doorways, scattered throughout the universe, each one potentially giving rise to an entirely new universe on the other side, complete with its own physical laws, its own history, its own long, patient unfolding toward complexity, and perhaps, eventually, its own form of life, looking upward at its own night sky, wondering, in turn, about its own origins. It is a staggering image to hold in the mind, even briefly. Somewhere, perhaps, scattered throughout the darkness of space, black holes may be quietly giving birth to entirely new realities, new universes, each one beginning its own long journey, from simplicity, toward whatever complexity it may eventually achieve. Whether this idea reflects something about the deep structure of reality, or whether it remains simply one of the more beautiful mathematical possibilities explored by theoretical physicists, it fits remarkably well into the broader living universe theme we have been exploring together, throughout this long, quiet night. Growth, development, reproduction, generation after generation, complexity, building upon complexity, across timescales that dwarf even the already vast scale of a single universe's own history. There is still more of this story ahead of us. In the next part of our journey together, we will continue exploring these ideas, moving further into the deep, patient unfolding of cosmic possibility. For now, let this rest quietly in the mind. Universes, perhaps, giving rise to other universes. Black holes, perhaps, serving as quiet doorways, rather than simple endings. And somewhere, within one particular universe, among what might be countless others, a small, quiet planet, still turning gently in the dark, carrying you, right now, drifting closer toward rest. Let's return to where we left off, with universes quietly giving rise to other universes, and follow that thread just a little further into the idea of cosmic selection itself. The notion of a reproducing universe, as we began exploring in the previous segment, is closely tied to that theory of cosmological natural selection. And it is worth sitting with the mechanics of that idea a little more closely now, because the word selection is doing quite a lot of work here. In biology, natural selection does not simply mean random change, occurring without direction. It means that certain variations, among many possible variations, happen to survive and reproduce more successfully than others, given the particular conditions of their environment. Over many generations, those successful variations become more common, simply because they are better suited to persist. Cosmological natural selection borrows this exact logic and applies it to universes themselves. Universes that happen to produce many black holes would, under this theory, produce many offspring universes. Universes that produce few black holes would produce few, or perhaps none at all. Over countless generations, then, universes with physics favorable to black hole formation would become more common, simply because they reproduce more successfully, not through any conscious intention, but through the same quiet, patient logic that shapes biological evolution here on Earth. It is a strange, elegant idea. Physical constants, quietly being shaped, generation after generation, not by any guiding hand, but by the simple, repeated advantage of certain configurations over others, echoing outward across a lineage of universes, stretching further than we may ever be able to observe or confirm. This is part of why some presentations of the theory draw so heavily on the language and logic of biology. Not simply as a poetic flourish, but because the thinkers proposing these ideas genuinely believe that universal evolution, in the broadest sense, might be guided by something resembling selection-like processes, the same fundamental logic that shapes the evolution of species, applied at a scale so vast it becomes almost impossible to hold an ordinary imagination. Once you allow yourself to follow this reasoning all the way through, a rather striking picture begins to emerge. In this broad model, a universe could be imagined as passing through recognizable stages, not unlike the stages of a living organism's own life. Birth, in the moment of its origin. Development, as it expands and cools, forming particles, atoms, stars, and galaxies. Reproduction, through the quiet mechanism of black holes, seeding new universes elsewhere. Aging, as stars gradually burn through their available fuel and structures slowly drift apart. And eventually, perhaps, something resembling death, as the universe reaches whatever final state its own physics dictates, whether that is a slow, cold fade into darkness, or something else entirely. Framed this way, a universe's entire history begins to resemble something closer to a single life, lived out across an almost incomprehensible span of time, rather than a purely mechanical sequence of physical events, unfolding without pattern or narrative. This reframing invites a deeper reconsideration of something we usually treat as an absolute, singular starting point, the Big Bang itself. In the more conventional scientific picture, the Big Bang represents the very beginning of everything. The starting point of space, time, matter, and energy, before which there is, by most conventional interpretations, no meaningful before to speak of at all. It is treated, in this traditional view, as a singular, isolated origin. The first moment. The beginning of the story, full stop. But certain versions of the living universe framework ask us to reconsider that assumption. They propose that the Big Bang might not represent an isolated, singular beginning at all, but rather, one stage, within a much larger, ongoing cosmic life cycle. Not the very first moment of all existence, but simply the first moment of this particular universe's own individual life, following, perhaps, the ending of some earlier universe that came before it. This reframing connects closely to another significant idea within cosmology, known as cyclic cosmology. Cyclic cosmology suggests that rather than following one single, one-way history, beginning with a Big Bang and ending, eventually, in some final, permanent state, the universe might instead pass through repeated phases, again and again, indefinitely. Expansion, followed eventually by contraction, followed by another beginning, in an endlessly repeating cycle, stretching backward and forward through time, without any single final ending at all. Under certain versions of cyclic cosmology, a universe expands for an enormous span of time, much as our own universe has been expanding for nearly 14 billion years. But rather than expanding forever, that expansion eventually slows, and reverses. The universe begins to contract, drawing back inward, growing hotter and denser, until it reaches some extremely compressed, high-energy state, not unlike the conditions believed to have existed at the very beginning of our own universe's history. And then, rather than simply ending there, in that dense, compressed state, the universe rebounds. It begins expanding once again, giving rise to an entirely new cycle, an entirely new universe, in effect, beginning fresh from that dense turning point. This particular mechanism, this idea of a universe collapsing and then rebounding into a new phase of expansion, has come to be known, quite evocatively, as the Big Bounce. The Big Bounce idea suggests, quite specifically, that a previous universe may have collapsed, reaching some extremely dense, high-energy state, before giving rise, through that rebound, to the universe we currently find ourselves living within. Under this view, what we call the Big Bang was not necessarily the absolute beginning of all existence. It may simply have been the moment of transition, the turning point, between the ending of one cosmic cycle and the beginning of the next. It is worth being honest, as we sit with this idea, that the Big Bounce remains a genuinely speculative proposal within physics. It is difficult to test directly, since any evidence from a hypothetical prior universe would need to somehow survive that extreme, compressed transition, in order to be detectable within our own universe today. But it remains a serious subject of ongoing theoretical research, precisely because it offers an elegant way of avoiding some of the deeper philosophical puzzles that come with imagining an absolute, singular beginning to all of existence. This cyclic framing connects quite naturally, and quite deeply, to our broader living universe theme tonight. Some thinkers explicitly draw this connection, linking the living universe idea to the possibility of a cyclic universe, repeating across what could potentially be infinite cosmic time. Because a cyclic cosmos, by its very nature, resembles a life process in a way that a purely linear, one-way universe never quite could. It is not simply a single, unrepeated sequence of events, beginning once, and ending once, and never occurring again. It includes recurring phases, expansion and contraction, growth and eventual collapse, followed, perhaps, by an entirely new beginning, echoing the pattern of what came before it. This rhythm of recurring phases, rather than a single, one-way history, is part of what makes the cyclic model resonate so strongly with the broader language of life, and growth, and renewal, that we have been exploring together throughout this long, quiet night. Even within a purely cyclic model, though, questions remain about what evidence, if any, might survive from one cycle to the next. And a few versions of these theories offer a genuinely fascinating, if still highly speculative, possible answer. Some researchers have proposed that the universe's history, stretching back through potentially countless prior cycles, might leave faint traces, embedded within the cosmic microwave background, that same faint, ancient light we mentioned earlier tonight, left over from the early universe, still detectable today, filling the sky in every direction we look. If a previous cycle's ending, and this current cycle's beginning, were connected through some kind of physical transition, rather than a clean, total erasure of everything that came before, then perhaps, subtle imprints of that transition, however faint, might still be detectable, hidden within the fine details of that ancient background light. This remains a difficult, contested area of research, and no clear, universally accepted evidence of this kind has yet been found. But the fact that scientists are actively searching for such traces, carefully studying the smallest fluctuations within the cosmic microwave background for any hint of what may have come before, shows just how seriously certain corners of physics have come to take these questions that, only a few generations ago, might have seemed to belong entirely to philosophy, or to speculation, rather than to careful, rigorous scientific inquiry. And finally, for this part of our journey together, one further extension of these ideas takes us beyond even the boundaries of a single universe altogether. One version of the living universe framework extends the entire concept outward, beyond any single universe, suggesting the possibility of something researchers sometimes call a living multi-universe, a vast collection of many universes, potentially infinite in number, that can evolve naturally over time, through processes resembling reproduction, and variation, and perhaps even something like selection, playing out across an almost unimaginably larger canvas than any single universe alone. Under this view, our own universe, with its nearly 14 billion years of history, its hundreds of billions of galaxies, its uncountable number of stars, and its at least one small, quiet planet capable of supporting life, would represent just one single thread, within an almost infinitely larger tapestry. One life, among countless others, each universe unfolding according to its own particular physics, its own particular history, its own particular journey from simplicity toward whatever complexity it may eventually achieve. It is, without question, one of the largest, most sweeping ideas we have encountered together so far tonight. And it remains, like so much of what we have explored throughout this long, quiet journey, deeply speculative, resting at the very furthest edges of what current physics can meaningfully test, or confirm, or even properly imagine. But perhaps that is, in its own way, part of the quiet comfort found within these ideas. Whether the universe truly reproduces through black holes, or cycles endlessly through repeated phases of expansion and collapse, or exists as one small thread within some vast, living multi-universe, these are, each of them, invitations to imagine reality as something larger, richer, and more deeply connected than it might otherwise appear, on an ordinary night, looking up at an ordinary sky. We have traveled a long way together already, through memory, mind, black holes, reproduction, and now, the quiet possibility of endlessly repeating cosmic cycles. There is still more of this story ahead of us, waiting patiently in the segments still to come. For now, let this rest quietly in the mind, the way the last light of evening rests gently along the horizon before finally fading. Universes, perhaps, cycling endlessly, one into the next. Faint traces, perhaps, hidden within the oldest light in the sky. And you, here, now, resting quietly within whatever vast, unfolding story this universe, or these countless universes, may ultimately turn out to be. Let's continue, gently, from that image of a vast, living multi-universe, because some thinkers have taken this idea and asked a more specific, more structural question. Not simply whether many universes might exist, but how a single universe might actually relate to whatever larger framework contains it. Some authors argue that a universe, our universe included, might be better understood not as a fully isolated, self-contained whole, but as something embedded, within a much larger framework. The word embedded is worth sitting with for a moment. It suggests something quite different from simple isolation. An embedded system is not floating alone, entirely disconnected from everything around it. It is nested, within something larger, shaped by, and perhaps dependent upon, the context that surrounds it, the way a single cell is embedded within a larger tissue, or a single tissue is embedded within a larger organ, or a single organ is embedded within an entire living body. If our universe is, in some sense, embedded within a larger structure, rather than existing as a single, isolated totality, complete unto itself, then many of the questions we have been exploring throughout this long night begin to take on a slightly different shape. Reproduction, development, even memory. These concepts become easier to imagine, not as strange properties belonging to an entirely self-contained universe, acting alone, but as properties that make more sense, once we allow for some larger context, surrounding and containing that universe, the way a body surrounds and contains each of its individual cells. This leads directly to a very specific, and rather striking, claim, made within a few versions of this theoretical framework. Some suggest that our universe may not actually be capable of true reproduction, of genuinely giving rise to new, offspring universes, unless it exists as part of some larger multiverse environment, capable of hosting and sustaining those newly created universes once they come into being. This makes a certain intuitive sense when you consider it carefully. A single living cell cannot simply reproduce into empty, undefined nothingness. It requires some surrounding environment, nutrients, space, the right physical conditions, some larger context, capable of receiving and sustaining whatever new structure emerges from that reproductive process. Some theorists propose that the same logic might apply at the cosmic scale. A single, isolated universe, entirely alone, with nothing beyond it, might not have anywhere for a newly created offspring universe to actually exist. But a universe embedded within some larger multiverse framework, some larger structure, capable of hosting many separate universes, existing alongside one another, would have somewhere for that reproductive process to actually unfold. This idea of a larger surrounding structure connects to another fascinating proposal, found within a few of these theoretical frameworks. The suggestion that the universe may have a built-in tendency toward creating isolated regions within itself, almost like compartments, nested inside some larger, living structure. This idea borrows, once again, from a very familiar biological image. A living body is not simply one undifferentiated mass of matter. It is organized into distinct compartments. Individual cells, each with their own boundary, their own internal environment, separated from neighboring cells by a membrane, even while remaining part of the same larger, coordinated organism. Some theorists propose that the universe, at the largest scales, might show a distantly similar tendency, a tendency toward compartmentalization, creating distinct, semi-isolated regions, each behaving somewhat independently, even while remaining, in some deeper sense, part of the same larger cosmic whole. This naturally leads toward a description some authors have used to characterize how the universe might actually behave at its largest and most fundamental level. Rather than assuming uniform behavior everywhere, following exactly the same rules, in exactly the same way, throughout the entire cosmos, some authors describe the universe as having both local domains and overarching life cycle rules, working together, side by side. In other words, under this view, different regions of the universe, or perhaps even entirely different universes, existing alongside our own, might each follow their own local physics, their own local conditions, their own particular unfolding history, even while all of them, together, remain subject to some larger, overarching pattern, some broader life cycle logic, shaping the whole system from a level beyond what any single region, or any single universe, could fully perceive from within. This is, in some ways, not entirely unlike the way individual organs, within a single living body, each maintain their own local processes, their own specific functions, their own particular rhythms, while remaining, at the very same time, coordinated within the larger rhythm of the whole body they belong to. Taking this comparison seriously, some of the more speculative models within this field extend the biological metaphor even further, proposing an image that is, admittedly, quite striking to hold in the mind. These models picture our entire universe, not simply as something loosely resembling a living system, but quite specifically, as something like a single cell, existing within a much larger organism, an organism composed, not of ordinary biological cells, but of countless universe-sized units, each one functioning, in some structural sense, the way an individual cell functions within an ordinary living body. Under this image, our universe, with its hundreds of billions of galaxies, its uncountable stars, its vast reaches of space and time, would represent something roughly equivalent, in scale and function, to a single, individual cell, nested within some almost incomprehensibly larger structure, composed of countless other universe cells, each one carrying out its own particular role, within some vast, cosmic-scale organism. This particular idea has come to be known, among some theorists exploring these questions, as the concept of self-replicating space cells. This framework proposes that the universe might contain repeating units, structures that echo, at a cosmic scale, the same basic architectural logic found within ordinary biological cells. A kind of cellular architecture, playing out not within living tissue, but across the vast fabric of space and time itself. Within these particular models, one very specific physical quantity becomes especially important: the cosmological constant. The cosmological constant is a term that appears within the equations describing the universe's overall expansion, a value connected closely to what is sometimes called dark energy, the mysterious force believed to be driving the accelerating expansion of the universe. In these self-replicating space cell models, the cosmological constant becomes significant, because it may influence whether particular cosmic regions are able to separate from one another, and evolve, somewhat independently, functioning as distinct, semi-autonomous units, much the way individual cells, within a larger organism, maintain their own distinct boundaries, even while participating within the shared life of the whole body they belong to. It is worth pausing to acknowledge, honestly and clearly, just how speculative this entire line of thinking remains. And yet, it is worth noting something equally important. The idea of universal self-replication is not simply confined to speculative fiction or informal philosophical musing. It is treated seriously enough, within certain corners of academic physics and cosmology, to be discussed as a genuine theoretical framework, explored through careful mathematics, published in peer-reviewed journals, and debated among researchers who take the underlying questions seriously, even while acknowledging how far these ideas currently sit from anything resembling confirmed, observational proof. Part of what allows this idea to be taken seriously within formal academic contexts comes from a particular mathematical approach, a way of defining self-replication that does not depend at all on biology specifically. Self-replication, under this more general, mathematical definition, can be described quite simply as a system influencing the future presence of similar systems. Notice how careful and how broad this definition actually is. It does not mention cells, or DNA, or any specifically biological mechanism at all. It simply describes a pattern, any pattern, where the presence of one system, in some way, increases the likelihood, or brings about the existence, of other, similar systems, appearing later. That is all the definition strictly requires. This broad, careful, mathematical definition turns out to be remarkably useful, because it allows scientists to compare lifelike behavior, across an enormous range of systems that have almost nothing else in common with one another. Crystals, for instance, can be described as self-replicating. In this broad mathematical sense, a growing crystal structure encourages the formation of further, similar crystal structures nearby, following the same underlying geometric pattern. Waves, moving across water or through other physical media, can sometimes trigger further, similar waves, under the right conditions. Cellular automata, simple computational systems following basic local rules, can produce patterns that replicate and spread across a grid, purely through mathematical logic, with no biology involved at all. And, of course, living organisms themselves, following the far more familiar, and far more complex, biological process of reproduction. What is quietly remarkable about this framework is that it allows all of these wildly different systems, crystals, waves, simple computer programs, and living things, to be compared and understood using the very same underlying mathematical language. Self-replication, understood this broadly, becomes less a special, exclusive property belonging only to biology, and more a general pattern that can emerge, in different forms, across many different kinds of systems, whenever the right underlying structure happens to be present. And it is precisely this broad, careful, mathematical framing that allows some theorists to seriously entertain the possibility that the universe itself, vast and strange as it is, might exhibit this same kind of pattern, not because the universe is secretly, literally alive, in any biological sense we would recognize, but because self-replication, understood mathematically, may turn out to be a far more universal, far more fundamental pattern than we ever initially assumed. Present, perhaps, not only within living cells, but within crystals, within waves, within the quiet logic of simple computational systems, and perhaps, at the very largest scales imaginable, within the structure and the unfolding of the cosmos itself. We have journeyed a long way together now, through embedded universes, cosmic compartments, self-replicating space cells, and the careful mathematics that allows scientists to compare lifelike patterns across an enormous range of different systems. There is still more of this story ahead of us, in the segments still to come. For now, let this settle quietly, the way still water settles after a stone has passed gently beneath its surface. Universes, perhaps, nested within universes. Patterns, echoing across scales so different from one another, that they hardly seem like they could share anything in common at all, and yet, somehow, quietly, mathematically, they do. Rest here for a while, in that quiet, layered immensity, and let yourself continue drifting, gently, toward whatever comes next. Let's pick up that thread once more, moving from the abstract mathematics of self-replication, towards something a little more concrete. Toward actual models, built and tested, however simplified, in an effort to understand whether these patterns could genuinely emerge from simple rules alone. Because some of the most interesting work in this field does not happen through pure philosophical speculation. It happens through careful, deliberate simulation. Some models of self-replication use entirely abstract, simulated universes, small, simplified, artificial systems, built specifically to study how replication might work, in principle, without needing to test anything on the scale of an actual, physical cosmos. This might sound, at first, like an unusual approach. How can a simple computer simulation tell us anything meaningful about the vast, physical universe we actually inhabit? But this is, in fact, a very common and very productive scientific method. When a system is too large, too complex, or too inaccessible to study directly, researchers often build simplified models instead, small, controllable systems that follow similar underlying logic, allowing them to explore fundamental questions without needing direct access to the full-scale phenomenon itself. In one particularly interesting study, researchers built something they described as a two-dimensional universe, entirely within a computer simulation. This was not, of course, an actual universe in any physical sense. It was a simplified, mathematical space, governed by a small set of basic rules, designed specifically to explore one central question. Could self-replication genuinely emerge from nothing more than simple, local interactions, without any outside designer deliberately building replication into the system from the very beginning? The results were quietly remarkable. Within that simplified, two-dimensional simulated universe, self-replication did emerge, not because the researchers explicitly programmed a replicate yourself instruction into the system, but because certain simple, local rules, interacting with one another, over time, produced patterns that reliably reproduced themselves, again and again, spreading throughout the simulated space. This finding connects to something even more specific and more evocative. That same kind of simulated model, researchers noted, showed a replication process that closely resembled a very familiar biological phenomenon, mitosis, the process by which a single living cell divides into two new, functionally identical cells. In the simulation, a particular structure would form, grow, and then, at a certain point, divide cleanly into two separate, similar structures, echoing, in a purely abstract, mathematical way, the same basic pattern found within actual biological cell division. This does not mean, of course, that the simulation was somehow secretly alive, or that it understood biology in any meaningful sense. It simply means that the underlying mathematical logic of division and replication, when expressed through simple rules, tends to produce patterns that look strikingly similar, whether you are watching a living cell divide under a microscope, or watching a simplified simulated structure divide within a computer program. This overlap between biological processes and simple computational systems has led some researchers to make a broader, more general claim. They suggest that the cosmos itself, vast and physical as it is, could reasonably be studied using the very same underlying logic used to understand self-replicating machines, or self-replicating simulations. Not because the universe is literally a computer, or literally a machine, in any simple sense, but because the mathematical patterns underlying replication, and growth, and structure, may apply broadly enough that they can meaningfully describe systems as different from one another as living cells, computer simulations, and perhaps, the unfolding structure of the universe as a whole. It is worth pausing here for a moment to place all of these speculative living universe ideas within a slightly wider and rather reassuring historical context. Because it is important to understand that cosmologists have long studied alternatives to whatever the prevailing, standard model of the universe happens to be, at any given point in scientific history. Questioning, revising, and proposing new ways of understanding the cosmos is not some strange, fringe activity reserved only for the more speculative corners of living universe theory. It is, in fact, a completely normal and deeply important part of how cosmology, as a scientific field, has always operated. The living universe idea, then, does not stand entirely alone, as some isolated, unusual departure from otherwise settled science. It sits, instead, within a much wider tradition of thoughtful, careful questioning about how the cosmos actually works, a tradition stretching back, in various forms, for well over a century. Some cosmology books make this point quite explicitly, noting that alternative models of the universe have existed for decades, long before contemporary discussions of a living universe ever began. The living universe idea, in other words, is simply one recent chapter within a much longer, ongoing history of non-standard cosmological thinking, a history filled with careful, serious scientists proposing genuinely different ways of understanding the structure, origin, and behavior of the universe as a whole. One especially well-known historical example of this broader tradition is something called the steady-state model. The steady-state model, proposed in the middle of the 20th century, offered a genuinely different picture of the universe than the one we generally accept today. Rather than beginning at a single, specific moment in time, as the Big Bang model proposes, the steady-state model suggested that the universe has always existed, eternally, without any true beginning at all. Under this model, the universe was understood to be continuously renewing itself, as galaxies moved apart from one another. Due to cosmic expansion, new matter was thought to be continuously created, in the empty space left behind, maintaining a consistent, unchanging average density throughout the universe, across all of time, past, present, and future. This is, in its own way, a beautifully elegant idea. A universe with no beginning and no ending. Simply existing, eternally, continuously renewing itself, forever. For a time, the steady-state model was taken quite seriously, as a genuine scientific competitor to the Big Bang theory. It was only later, through the discovery of specific observational evidence, including that same cosmic microwave background radiation we discussed earlier tonight, that the scientific community gradually moved away from the steady-state model, in favor of the hot Big Bang theory, which fit the accumulating observational evidence considerably better. The steady-state model is simply one example, among several, of alternative cosmologies proposed throughout the history of the field. Several such alternative models were developed, historically, specifically to address particular scientific puzzles that scientists were grappling with, at various points in time. Some models were proposed to explain redshift, the observed phenomenon where light from distant galaxies appears shifted toward longer, redder wavelengths, generally interpreted as evidence of the universe's ongoing expansion. Other models grappled with questions surrounding matter creation. Where, exactly, does new matter come from, if the universe is either continuously expanding, or continuously renewing itself? And still other models focused specifically on the origin of cosmic structure, trying to explain, through various different mechanisms, how the universe moved from an early, relatively uniform state toward the rich, complex structure of galaxies and galaxy clusters we observe today. The very existence of all of these historical alternatives, the steady-state model, and others like it, reveals something important and worth sitting with quietly as we continue moving through this long, thoughtful night together. Cosmology, as a field, has never been completely settled. Not in the past, and, in certain important respects, not entirely even now. Even though the standard hot Big Bang model remains, by a wide margin, the dominant, most well-supported view among cosmologists today, supported by an enormous body of careful, converging observational evidence, it has never been treated as some final, unquestionable truth, closed off entirely to further inquiry or further refinement. This ongoing openness, this willingness to keep questioning, keep testing, keep proposing new ideas, even against the backdrop of a generally well-supported standard model, is precisely why this debate has persisted across so many decades and continues to persist even now. No single cosmological model, including the standard hot Big Bang model itself, has yet managed to fully answer every major question surrounding the universe's ultimate origin and its large-scale behavior across the full span of cosmic history. Certain deep puzzles remain. The nature of dark matter. The nature of dark energy. The very earliest moments, right at the boundary of the Big Bang itself, where our current physical theories begin to break down and stop providing clear, reliable answers. It is precisely within these remaining gaps, these unresolved questions, that speculative ideas like the living universe framework continue to find room to breathe, and to grow, and to invite our imagination forward, even while remaining, quite honestly, unproven, and quite far from settled, scientific fact. We have covered a great deal of ground together, across this long, quiet night. From simulated two-dimensional universes, dividing like living cells, to the steady-state model, imagining an eternal, ever-renewing cosmos, to the honest, ongoing uncertainty that continues to surround even our very best current understanding of the universe's origin and structure. There is one more part of this journey still ahead of us, waiting patiently in the segment still to come. For now, let this settle quietly, the way it always does, at this point in our journey together. Alternatives, considered and set gently aside. Questions, still open, still unresolved, stretching back across decades of careful scientific thought. And you, here, now, resting quietly, as this long, unfolding story continues to drift, gently, toward whatever comes next. Let's continue from where we paused, with that honest acknowledgement of ongoing uncertainty, and look a little more closely at the shape of that uncertainty itself, at what exactly remains unexplained, within our current best understanding of the cosmos. Because it is worth saying clearly, and without any sense of alarm, that the current standard cosmological picture, while still dominant, still overwhelmingly well supported by the evidence, does not explain every observational puzzle perfectly. This is simply the honest, ordinary state of any healthy scientific field. No model, however successful, however well-tested, ever manages to account for absolutely everything, with perfect precision, on the very first attempt. Science moves forward, patiently, Through this ongoing tension between what a model successfully explains and what it still struggles to account for. The standard cosmological model itself, the one most cosmologists compare all of these alternative ideas against, is often referred to by a particular name, lambda CDM. That first symbol, the Greek letter lambda, represents the cosmological constant, connected to dark energy, into the accelerating expansion of the universe. The letters that follow, C, D, M, stand for cold dark matter, that invisible, gravitationally significant material we discussed earlier tonight. Together, lambda CDM describes a universe built around a small number of core ideas: gravity, shaping structure at every scale, a steady, ongoing cosmic expansion, and a hot, dense early universe, cooling and evolving, over billions of years, into the rich, structured cosmos we observe today. This model has proven remarkably successful at explaining an enormous range of observations, gathered from many different, independent lines of evidence. And yet, as we touched on already, certain deep questions remain. And it is precisely within that space of remaining questions that this whole landscape of alternative cosmological ideas continues to live, and grow, and quietly persist. It can be helpful, at this point in our journey, to step back and see this landscape of alternatives a little more clearly, rather than simply as a scattered collection of unrelated, speculative ideas. Some alternative cosmology papers, in fact, organize these ideas quite deliberately, along something like a spectrum, ranging from very small, modest changes to the standard model, all the way out to fully non-standard theories that depart from the conventional picture almost entirely. Picture, for a moment, a long, gentle gradient. On one end, sit ideas that accept nearly everything about the standard lambda CDM model, while adjusting only one small piece of the puzzle. On the far other end, sit ideas that reimagine the universe almost completely, proposing entirely different foundational assumptions about how reality itself is structured. And scattered along the length between those two extremes, sit a wide range of other proposals, each one modifying the standard picture to a different degree. Some of these alternative cosmologies sit quite close to that conservative end of the spectrum. They try to keep most of the standard model intact, while changing only certain specific assumptions. Perhaps altering our understanding of inflation, that brief, extraordinarily rapid period of expansion believed to have occurred in the universe's earliest moments. Or perhaps adjusting our current understanding of dark matter, without discarding the broader framework of the standard model altogether. Several such models exist, each one modifying only one particular piece of the standard picture. Some models adjust our understanding of inflation. Others adjust the properties or behavior of dark matter. Still others focus on dark energy, that mysterious force believed to be driving the universe's accelerating expansion, or on the precise number of neutrinos, those famously elusive, nearly massless particles, produced in enormous quantities throughout the universe's history. Each of these models represents a fairly modest departure from the standard picture, adjusting one particular variable, while otherwise leaving the broader framework largely intact. Moving further along that spectrum, other models introduce considerably larger, more fundamental changes. Some propose a universe where physical constants, the fixed numerical values that govern the strength of gravity or the behavior of electromagnetism, are not actually fixed at all, but instead vary gradually over vast stretches of cosmic time. Others propose an entirely different underlying law of gravity altogether, different from the framework laid out by Einstein's general relativity, which currently forms the gravitational foundation of the standard cosmological model. This particular idea, that physical constants might vary over time, connects in an interesting way back to our broader living universe theme tonight. If the fundamental constants of physics are not fixed, unchanging values, but instead shift gradually across cosmic history, then the universe, in a very real, very literal sense, becomes more dynamic and more developmental than the standard picture typically assumes. Not simply a fixed stage, upon which the same unchanging physical rules play out indefinitely across billions of years, but something closer to an evolving system whose most fundamental properties are themselves capable of shifting and changing over time. Other, still more radical departures from the standard model propose something called an inhomogeneous universe. This is, admittedly, a more technical term, but the underlying idea is fairly easy to grasp intuitively. The standard cosmological model generally assumes that the universe, on the largest possible scales, is broadly uniform, roughly the same density, roughly the same structure, in every direction we look, once you average out over large enough regions of space. This assumption, sometimes called the cosmological principle, has been enormously useful for simplifying the mathematics involved in modeling the universe's overall behavior. An inhomogeneous model challenges that assumption directly, proposing instead that large-scale structure may not actually be uniform everywhere, but might vary, in more significant ways, across different regions of the observable universe. If true, this would represent a genuinely significant departure from the standard picture, with potentially far-reaching consequences for how we interpret many of our most fundamental cosmological observations. It remains, currently, a minority position within the field, but it continues to be studied and debated seriously by researchers exploring the outer edges of current cosmological thinking. Beyond these particular ideas, the full landscape of alternative cosmologies includes a fascinating range of other, more specifically named proposals. Plasma cosmology, for instance, proposes that electromagnetic forces, acting on the vast quantities of ionized plasma found throughout the universe, may play a considerably larger role in shaping cosmic structure than the standard model typically assumes, which focuses primarily on gravity as the dominant structuring force. Quasi-steady-state cosmology represents a more modern revival and revision of that older steady-state idea we discussed in the previous segment, attempting to address some of the observational challenges that led scientists to largely abandon the original steady-state model decades ago. And hypersphere universe models propose a very particular geometric shape for the universe as a whole, imagining it as a kind of four-dimensional analog to an ordinary, three-dimensional sphere, a shape that is, admittedly, quite difficult to visualize directly, but mathematically coherent and worth taking seriously within the broader landscape of cosmological possibility. One further alternative worth mentioning specifically is something called the Milne model, named after the physicist who first proposed it, in the early 20th century. The Milne model is often discussed alongside these other cyclical and quasi-steady-state ideas, as it offers yet another distinct way of imagining the universe's overall structure and expansion, differing in its underlying assumptions from the standard lambda CDM picture, though, like most of the alternatives we have discussed tonight, it has not gathered the same broad observational support that has made the standard model the dominant view among cosmologists today. Taken together, this entire landscape, modest adjustments, larger departures, entirely reimagined geometries, and named historical alternatives, stretching back across the better part of a century, reveals something quietly reassuring about the nature of scientific inquiry itself. The universe remains, in certain deep and fundamental ways, genuinely mysterious. Not fully mapped. Not fully understood. Still inviting careful, patient, rigorous questioning, from many different angles, by many different researchers, each one contributing a small piece to a much larger, still unfolding picture. The living universe idea, which has carried us through so much of this long night together, sits comfortably within this same broader tradition. Not as an isolated, unusual fringe idea, disconnected from serious scientific thought, but as one thread, among many, within a rich, ongoing history of careful, imaginative questioning about what the universe actually is, and how it actually behaves, at the very largest scales we can observe, or even imagine. We are drawing close now, to the final part of our journey together tonight. In the segment still ahead, we will bring this long, unfolding exploration to its close, gathering together the many threads we have followed, throughout this quiet night, into something resembling a gentle, closing perspective. For now, simply rest here a while longer, in this landscape of quiet alternatives, and careful, ongoing questions. Constants that might shift, ever so slightly, across billions of years. Structures that might vary, subtly, across the vastness of space. And a universe, still holding its deepest secrets closely, even now, even after a century of patient, careful study, inviting us, gently, to keep listening, and keep wondering, a little while longer. This is the final stretch of our journey together tonight, and it is worth moving through it slowly, the way you might walk the last few steps of a long, familiar path home. We left off in that landscape of alternative cosmologies, and there remain a few more of these unusual proposals, sitting even further out along that spectrum we described. Some of them push right up against the very edges of what conventional physics finds comfortable. Among these more unusual proposals is something called a zero-active mass universe. This is a fairly technical idea, but the underlying image is worth holding on to gently, even without fully grasping the mathematics behind it. In general relativity, mass and energy do not simply attract, the way ordinary gravity is often described in simpler terms. Under certain conditions, they can also exert a kind of pressure that behaves almost like a repulsive force, pushing outward rather than pulling inward. A zero-active mass universe describes a scenario where the overall cosmic fluid, the combined mass and energy filling the universe, produces a very unusual overall gravitational effect, one where these ordinarily competing tendencies, attraction and repulsion, balance out in an unusual way, producing behavior quite different from what we observe in our own universe. It is a strange, mathematically elegant idea, existing mostly as a theoretical curiosity, rather than a serious contender for describing our own actual universe. But it illustrates just how far theoretical cosmology is willing to explore, even into configurations that seem to defy our ordinary intuitions about how gravity is supposed to behave. At the very farthest extreme from standard cosmology sit static models, proposals that reject something most of us have come to take for granted throughout this whole exploration: the usual interpretation of redshift as evidence of cosmic expansion. We mentioned redshift earlier tonight, that observed phenomenon where light from distant galaxies appears shifted toward longer, redder wavelengths. The standard interpretation treats this as direct evidence that space itself is expanding, stretching the wavelength of light as it travels across vast cosmic distances. Static models propose something quite different. They suggest the universe might not actually be expanding at all, and that redshift, instead, might be explained by some other physical process entirely. One such proposal is the idea of tired light. Under this hypothesis, photons, the particles of light traveling toward us from distant galaxies, might simply lose energy gradually, over extremely long distances, through some process unrelated to cosmic expansion. As a photon loses energy, its wavelength would lengthen, producing exactly the kind of redshift we observe, without requiring space itself to actually be stretching or expanding at all. It is worth being honest and direct here. The tired light hypothesis, and static universe models more broadly, have not found strong support within the broader astronomical community. Multiple independent lines of evidence, beyond redshift alone, consistently point toward genuine cosmic expansion, and these static alternatives have struggled to account for that full body of evidence, as successfully as the standard expanding universe model does. But the fact that serious researchers have explored, and continue to occasionally revisit, even this most fundamental of assumptions, tells you something important about how cosmology actually operates as a field. Nothing, not even the most basic, seemingly settled observations, sits entirely beyond the reach of careful, ongoing scrutiny. A few alternative theories, among the many we have discussed tonight, are specifically designed to fit certain particular observations better than the standard lambda CDM model does, at least in isolated cases. Perhaps a specific model handles one particular puzzle, some detail in the distribution of galaxies, or some subtle feature in the cosmic microwave background, slightly more elegantly than the standard picture manages. But it is important to say clearly that none of these alternative models has matched the standard model's overall explanatory reach. Lambda CDM remains dominant, precisely because it successfully explains such an enormously wide range of different observations, all at once, using a relatively small and consistent set of underlying assumptions. Individual alternatives may occasionally outperform it, in some narrow, specific case. But none has yet managed to match its broad, comprehensive success, across the full range of cosmological evidence we currently have available. It is worth emphasizing something important here, as we bring these threads together. Several researchers, working seriously within this field, stress that these alternative cosmologies are not simply philosophy, disconnected from rigorous science. They are not idle speculation, floating free of any real-world testing. These models can be, and often are, compared directly against actual astronomical observations, in principle, using the same careful, rigorous methods used to test the Standard Model itself. This matters a great deal for how we should understand everything we have explored together tonight. The living universe idea, and the many alternative cosmological frameworks we have discussed alongside it, are not simply comforting stories, offered without any real scientific grounding. They exist, for the most part, within a genuine scientific tradition, one where ideas are expected, eventually, to be tested and compared against careful observation and evidence, even when that testing remains difficult, or incomplete, or still years away from delivering a clear answer. And in fact, some of that testing may not be too far off. Next-generation astronomical surveys, and new scientific experiments, currently being planned and developed, are expected to test some of these new cosmological paradigms within the next 5 to 10 years. New telescopes, new instruments, new ways of gathering and analyzing cosmic data promise to sharpen our picture of the universe considerably in the years just ahead. Some of the open questions we have sat with together tonight may find clearer answers sooner than we might expect. This brings us, gently, toward a kind of closing thought for this long, patient exploration we have shared throughout tonight's journey. Because cosmology still holds unresolved questions about dark matter, about dark energy, about the earliest moments of the universe's history, about whether space itself began once, or has always existed, cycling endlessly through repeated phases, ideas about a living, or evolving, universe continue to attract genuine interest as possible frameworks for pursuing deeper explanation. Not because these ideas have been proven true, but because the questions they attempt to address remain genuinely open, genuinely unresolved, inviting new perspectives, new metaphors, new ways of thinking that might eventually lead toward better, clearer answers. These alternative frameworks matter to the living universe discussion specifically because they demonstrate something important. They show that cosmology, even now, even after a century of remarkable scientific progress, still has room for models where the universe behaves in less mechanical, more process-like ways. The universe we have explored together tonight is not simply a fixed, static machine, ticking forward according to unchanging, predetermined rules. It is something considerably stranger and considerably more open than that, a system still being understood, still being questioned, still capable of surprising the very people who study it most closely. It is worth noting, as we come to a close, that recent writing on this subject suggests something quietly significant is happening within the broader intellectual landscape surrounding these ideas. The concept of a living universe is gradually moving from what was once fringe speculation into a more serious, more sustained conversation among people working across physics, biology, and the still emerging field of complexity science. This does not mean the idea has been proven or widely accepted as established scientific fact. But it does mean the conversation itself is being taken more seriously by more careful thinkers than it perhaps once was. And so, we arrive, gently, at the end of this long, quiet exploration. Whether the universe is truly alive, in any meaningful sense of that word, remains genuinely unknown. We have followed this question through analogy, and through metaphor. Through dark matter, described as an unseen skeleton. Through cosmic expansion, compared to growth in metabolism. Through black holes, imagined as quiet doorways to new universes. Through cyclical cosmologies, and self-replicating space cells, and simulated universes, dividing like living cells within careful mathematical models. Through panpsychism and biocentrism, and the strange, unresolved role that observation itself may play in shaping the reality we experience. None of this constitutes proof. Nothing we have explored together tonight settles the question in any final, definitive way. And perhaps that is exactly as it should be. Because what this question does, more than anything else, is push scientists, and philosophers, and quiet, curious minds like your own, listening somewhere in the dark right now, toward new ways of thinking about reality itself. Toward new metaphors. New frameworks. New willingness to imagine the universe, not simply as a cold, mechanical backdrop, indifferent to everything happening within it, but perhaps, just perhaps, as something closer to a process. Something unfolding. Something still becoming, whatever it is ultimately meant to become. You do not need to resolve this question tonight, or any night. It is enough, simply, to have sat with it for a while. To have turned it over, slowly, the way we might turn over any old, quiet mystery, letting the light catch it differently, from each new angle we consider. Somewhere above you now, whether you can see it or not, the same universe continues turning, patiently, the way it has for nearly 14 billion years. Stars quietly living out their long lives. Galaxies drifting slowly through the dark. Matter and energy, flowing endlessly, from one form into another, across a canvas of time too vast to ever fully hold in mind. And somewhere within all of that vastness, here, now, resting quietly in the dark, is you. One small, quiet part of whatever this unfolding story ultimately turns out to be. Whatever the universe is, alive, or simply behaving as though it might be, it carries you gently within it, tonight, and every night. So let yourself rest now, fully, and drift, slowly, into whatever comes next, carried, as you always have been, by the same patient, endlessly unfolding universe, that has been telling its long, quiet story, since the very beginning of time itself. Sleep well.